Earlier on, when we started sort of introducing quantum mechanics, one of the things that we defined was that a wave or a particle is defined by a wave. And automatically this sort of creates issues when dealing with values that are traditionally definite in normal physics, things like position and momentum. So now in 1.6 we're sort of going to analyze this idea of representing a particle using a wave function more literally and sort of develop an analogy of some of the implications of doing something like this. So first off, let's sort of very briefly give a summary of sort of the fundamental idea behind indeterminacy in quantum mechanics. So wave function gives indeterminacy to traditionally definite values like position. And what we mean by this is that, well, if we define the location of a particle by a wave function, now the particle has a probability of being in a given series of locations. It has a very high probability of being in some interval between A and B. It has a low probability of being in some other interval between C and D, and so on and so on. However, it is not physically possible for us to actually define exactly where the position of the particle is. So let's sort of actually analyze this from a literal standpoint. And let's say that we have this rope that's attached to a wall at one end. So let's say I have this rope, and let's say that there's some person here. Let's say I'm at the other end, and let's say that I'm sort of shaking the rope. So if I sort of wave the rope up and down, it's going to end up following sort of this sort of sinusoidal motion. So something like this. Actually, that's not quite correct because I have to match the end conditions of the rope. So something like this. And as I sort of just continue to wave the rope up and down, the rope will form this sort of sinusoidal pattern about the center point. And obviously, just from looking at this, hopefully you realize that it doesn't really make sense for us to sort of ask what the position of the wave is. The wave is sort of everywhere along this interval from like the start, which is me, all the way to the end, which is the wall. And if we sort of take this analogy and take it to the logical conclusion, which is to have an infinitely long rope that goes on forever, and then I shake this rope up and down, well, in that case, evidently the position of the wave that I have created is technically over all of space, not just at any given point. On the other hand, the wave does have values that we can define exactly, and one of these is actually wavelength. So let's sort of define that first. So we can't determine the exact position of the wavelength of our wave, but we can determine something. Well, actually, let's do this. We can't determine the exact position of our wavelength. However, we can determine the wavelength of our wave. And measuring the wavelength is merely a matter of sort of putting a camera in front of this whole setup, taking a picture, and then sort of just analyzing the distance between one peak and another peak. So if I were to take a picture of this whole setup and then put it in some sort of photo analyzer or software or whatnot, I could measure the distance between one peak and the other peak, and this distance would be the wavelength, lambda. Now, let's sort of analyze a second scenario where instead of continuously moving our wave up and down, I only just jerk the wave sort of once. So instead, I sort of, oops, that's not what I want. Instead of sort of creating a continuous wave that goes on forever, what I'm going to do instead is I'm going to just jerk the rope once really hard. And what will happen is that it'll create this sort of pulse And hopefully you are familiar with this from wave mechanics back in classical, but this pulse will basically move forward with some speed v. So evidently in this case, by creating a pulse, we are now able to define a definite position, or not definite, but able to define a more accurate position and velocity compared to before. Because this pulse does have an actual, or not an exact position, but a pretty nice localized position. The pulse is its x position, or wherever its position is a sort of, we can sort of separate it or isolate into this green interval here. We know that the wave is somewhere within this interval, and it also has a definite velocity. It moves forward at some speed, and we can always just take a recording and sort of measure that with some sort of program or whatnot. So evidently, if we sort of do this pulse, we are now able to sort of tell the position of our wave more accurately. However, the problem with this is that the trade-off, let's return to blue, the trade-off of making a pulse is that we are now no longer sure of the wavelength. Because before, when I was sort of waving this rope up and down, and I had this very nice wave, I could tell pretty accurately what the wavelength was because I have the entire sort of waveform of my rope. Whereas in the second case, where I'm only just moving the rope once and sort of pulsing it very quickly, I can no longer tell what the wavelength actually is. I don't even know what the waveform looks like. You know, I can make an estimate. I can say, okay, well, the waveform probably would look something like this if I were waving this thing repeatedly, and I could make an estimate and say, okay, well, the wavelength is roughly this interval, but this is obviously much less sort of accurate compared to before here, where I can just directly measure the distance between two pulses. Here, I sort of have to guess what that is, and because of that, it's less accurate. And what'll happen is that if I make this pulse even smaller, if I sort of jerk the rope in an even at an even sort of sharper angle, me right here on this side, and if I jerk this rope at an even sharper angle so that it sort of takes on an even sharper peak, well, now sort of the interval over which the wave is defined, its position interval, is even smaller. I know the position even more exactly. However, now I know the sort of waveform even less. You know, this probably looks something like this, maybe. And the wavelength is even more inaccurate. My measurement of the wavelength in this scenario is even more inaccurate. And sort of as I go to infinite, as I sort of make this pulse infinitely peaked about a definite position, as I sort of make this pulse so narrow that I finally do gain the ability to define the position of the pulse exactly instead of using an interval, at that point I do not know anything about the wave function or of the wavelength, because at that point sort of what you have instead is just sort of something that looks like this. And at this point, well, I know that my position is exactly here, but now I don't know anything about my wavelength. You know, even if I were to like sort of try to try to like create what I think the complete waveform would look like, it would be just this indistinguishable mess, and I would not be able to actually figure anything out from it based on this zoom level. And if I were to like sort of zoom in, I would once again sort of have this same scenario where I have like once again this interval of position of my pulse, and as I zoom in more and more, the interval gets larger and larger, and if I wanted to make the position more and more definite, I would have to make the pulse smaller, thus making my knowledge of the wavelength of this function less and less accurate. So evidently, for waves, there is a trade-off between knowing position and knowing wavelength. The better, or the more accurately we know one value, the less accurately we know the other. So in the case where I sort of know the wavelength with infinite accuracy, that would correspond to having like an infinitely long rope going all the way through, stretching all the way through space, and in that case the position is theoretically also is an infinitely long interval. So because of that, we know absolutely nothing about the position. And then in the other extreme end, where we know the position exactly, this pulse is an infinitely thin line, so we know nothing about the wavelength. So we have this sort of trade-off, evidently. So this implies that there's also some other similar analogous trade-off in terms of two values in quantum mechanics for particles. So as it turns out, there is, and that is what is called the uncertainty principle. And to sort of get to it, one of the things that we have to resolve is that we can link the wavelength to momentum using de Broglie's wave equation. So de Broglie's wave equation is basically a equation which allows us to relate the momentum of a particle to its wavelength. De Broglie basically came up with this theory that particles exhibit wave properties. If you're not familiar with this, I would suggest you sort of touch up this on your own time. This is has to do with sort of the precursor to quantum, which is sort of particle physics, I guess you would call it. And basically the equation that he gives is that the momentum of a particle is equivalent to 2 pi times h bar, all divided by the wavelength of that equivalent particle. So this is sort of the reason why that when we were dealing with operators way back, we sort of started by defining position and momentum instead of position and velocity, because momentum actually comes up a lot more often in many of our calculations compared to velocity, and it sort of just makes our life easier to deal with position and momentum instead of position and velocity. This is one example where using momentum just sort of simplifies the process somewhat. So evidently in the case of particles, instead, so for waves, the trade-off is between position and wavelength, but it doesn't really make sense to define the wavelength of a particle. So instead, in quantum mechanics, when we're dealing with a particle, what we say is that for QM, the trade-off is between position and momentum. Position and momentum. So apparently for a particle, which I have defined a wave function for, in that scenario, sort of the trade-off in knowledge is between the position of the particle and the momentum of the particle. The more I know about the position of a given particle, the less I know about its momentum, and vice versa. And as it turns out, this trade-off is what is known as the uncertainty principle, which quantitatively gives us a lower limit to the product of the standard deviation of momentum and position. So what the uncertainty particle, mathematically, what it tells us is that the standard deviation of the position of a particle times the standard deviation of the momentum of a particle has to be greater or equal to h bar over 2, where h bar is a constant. So this is some sort of numerical limit that we cannot surpass. And evidently, this is very weird. We are used to, in classical mechanics, sort of dealing with position and momentum as definite things. We're used to being able to say this particle is exactly in this position and is traveling with exactly this velocity and therefore exactly this momentum. However, apparently in quantum mechanics, when we introduce indeterminacy, there's actually a limit to how much we can know something. And apparently this limit is not independent intrinsically tied to individual values. It's not just a matter of not being able to tell position exactly, or not being able to tell momentum exactly, or not being able to tell energy exactly, but rather there are apparently certain values, in this case position, momentum, but maybe there are others that are apparently intrinsically linked to each other in such a way that we cannot actually know both of them simultaneously. Rather, there is sort of this resolution limit that we sort of approach, and as we get closer, it becomes eventually impossible to tell our system with any higher resolution. I cannot know exactly the position and the momentum, or in fact, I cannot even know the position and momentum within a small enough interval such that their standard deviations multiplied is greater than this numerical value. Now, granted, h bar over 2 is a very large numerical value, however, or not a very small numerical value, which is why in classical mechanics it basically doesn't matter. However, in quantum, since we are dealing with sort of subatomic systems, this does become a significant distance, and because of that, sort of does play a role in any sort of system analysis that we actually do. One final note here, I did sort of introduce this formula, sigma x sigma p is greater than or equal to h bar over 2, sort of without warning. Griffiths sort of does this as well, and unfortunately we actually can't derive this equation until way later on when we start introducing linear algebra and operators, and start working with operators sort of in more detail. And as a result of that, this is sort of once again another thing that Griffiths throws at us that we simply have to accept, because there really isn't a way for us to prove this as a fact until significantly later on in the book.